Okay, as promised, now we need to focus on the next type of math problem that we've got to do. And this is our second equation. Again, you will be given these equations, you do not have to memorize them. But E is going to stand for energy in joules. If you remember back in thermo, we talked about Q being equal to heat, which we also had for joules. So we see some overlap here. V is the same frequency we had before. It's either going to be seconds to the -1 or hertz. Remember, seconds to the -1 is 1 over s. And then we've got another constant, which you will be given. This is called Planck's constant. We saw Planck in the last section where he essentially did a whole lot of math to come up with packets or quantum of energy, and his constant is 6.626 times 10 to the -34 joules times seconds. And again, you will be given that. You will not have to memorize that for tests and quizzes. Okay, so let's do some practice problem stuff here. We know, what are they telling me? Well, they're telling me that the frequency of a gamma ray is 6.0 times 10 to the 22nd hertz. And I'm going to put 1 over s just as a reminder that that's what hertz are equal to. The unknown here is E for energy. So we are going to use the E equals hv equation. Remember, the other equation that we have in this unit is the speed of light is equal to wavelength times the frequency. So we do have a common variable, and you'll see how that comes into play in some of our practice problems. And the other thing that we also know is Planck's constant, 6.626 times 10 to the -34 joules times seconds. So it makes it pretty simple. We just plug and chug here. We've got the known and unknown, we've got the equation, we've got 6.626 times 10 to the -34. Now I'm at a space, so I'm going to go on to a second line, but I'm multiplying here, not dividing. 6.0 times 10 to the 22nd. So on my calculator, 6.626 times 10 to the -34. Multiply, don't forget parentheses, especially on the second number. Sorry, it's 6.02 times 10 to the 22nd. If I look at my data only had 2 significant figures. That's all my answer is going to have. My final answer should be 4.0 times 10 to the -11th joules. Always a good idea to plug this in on your calculator just to make sure you can get the right answer. Because exponents just add a different factor. Now, the other variable that you would be solving for in this equation is frequency. And just to show you what that would look like, if you're not great at algebra, just like I mentioned before, sometimes the easiest thing is just to memorize all the different variations of an equation. If I had E equals hv, to get V by itself, I would have to divide both sides by Planck's constant. So if I'm solving for V, I take the energy and I divide it by Planck's constant. So if you're not great at manipulating equations, you may just want to memorize that. Okay, here comes Einstein's contribution. Thinking about the photoelectric effect, which if you remember from the last video, photoelectric effect is when we have a metal plate and we sent in waves of energy, and out came particles or electrons, which was very different. We essentially took waves and we got particles. So what Einstein's suggestion was that light can be also be viewed as a stream of particles. And at the time, this was a pretty radical idea, and there's way more science that goes into it, and we ask you to make some big leaps in this section and just kind of accept the final result, because we're not going to get into all the details. But ultimately what this came up to be is the dual nature of light theory. And the dual means two. So the two ways that we can view light is like a particle or like a wave. And again, what you kind of need to think of, you've seen me draw this picture before, you can think of light as either a stream of particles or a wave, depending on which way you need to interpret it in order to make sense. Okay? All right, now along with the photoelectric effect, a few other definitions. We have the word photon. A photon is a particle of electromagnetic radiation that has no mass but has 1 quantum of energy. Again, I don't want you to get too caught up in this no mass thing. You know, lots of leaps here, but it does have 1 quantum or 1 packet or a certain amount of energy. That's what a photon is going to carry. And energy and frequency are going to be directly related. Okay, and again, we'll talk about this from the perspective of the electromagnetic spectrum. As energy of something goes up, the frequency of the wave or the radiation also goes up. And if we were to draw their relationship on a set of axes, you would have a straight line that goes through the origin. Okay, so they are directly related. All right, now comes our second experiment that did not make sense based on the wave theory of light, and that is the hydrogen line emission spectrum. And you're going to see a sample of this in class. So again, this first go round, don't get too caught up if it's not rock solid. You're going to get this feedback later. Okay, we got to define some things. Ground state is the lowest energy state of an atom. This is essentially where we've talked about atoms. This is where atoms want to be. They are happiest at their lowest energy possible. And you're going to see me refer to this as them being happy a lot, particularly the rest of this quarter. An excited state is just that. If something is excited, it has higher potential energy than the ground state. And usually we have to or the environment has to force that to happen. And if we put energy, let's see if I can get this to work here. If we put energy, I don't know why it's disappearing, on the y-axis, okay? And if you think about it this way, every time that we increase the energy, we usually have to do that by running electricity through it, setting it on fire, but doing something that can generate excitement or higher energy. What happens is that an atom will want to come right back down to ground level. Okay, I know it's kind of tough to see, but it wants to come right back down. And that's going to be an important process of this. Now, an line emission spectrum is a series of wavelengths of light that are created when a visible portion of light from excited atoms is shined through a prism. Excuse me, I got a little bit of a cold here. And again, we're going to see this. And essentially, every element has its own line emission spectrum. And it's kind of a intensive property, meaning that it does not depend on how much matter is present, but it allows us to identify certain elements. And we're talking about hydrogen for this first part. Okay, so what they expected to happen is that scientists using classical wave theory expected atoms to be excited by whatever energy they absorb. They expected this to occur on what's called a continuous spectrum. And if we define continuous spectrum, it's just the emission of the continuous range of frequencies on the electromagnetic radiation. So all of those different, where we had the AM on one end and the FM and the microwaves, everything got smaller, X-rays, gamma, et cetera, et cetera. But this whole thing was going to excite atoms. And that's not what happened. Just like when Rutherford expected everything was going to pass through the atom and it didn't go that way, they had to explain it. Same thing happens here, is that what they expected to happen, so here's my hydrogen on fire. Again, we have to increase the energy. We pass it through a small slit, really just, to focus the light. And then we pass it through a prism, which if you've ever seen light pass through a crystal or anything that's clear and it separates it, you've seen the same thing. Now, what they expected to happen was that they would see the entire visible light spectrum, right? Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. But what they saw was only specific frequencies. And again, you'll see this in class, and here you see the blue and the yellow and the red, but they didn't give off everyone in between, only certain ones. And that was a really big thing, because essentially we had the same situation where we hit it with something that was a wave, and it separated into parts and pieces. And so they had to explain why. That was kind of tough to do. But essentially, current quantum theory, yes, remember, theory is an explanation. We are going to give you about the smallest amount of quantum information as we possibly can. You don't have to know all the background. You just have to know the end result and the explanation. So, quantum theory came along with a new theory of an atom, and they try to explain that. So, what we have is, again, here is the hydrogen that this particular case, when hydrogen has electricity running through it, it kind of gives us this neon color, and we'll see this in class. We pass it through a prism, or we pass it through a slit, we get through the prism, and it separates it into these specific bands. And we'll see a couple of these so that we can see the difference. But again, we had continuous, light that was separated into pieces, and we had to explain that. which is different. Now here's quantum theory's explanation. Okay, so here's my excited electron. All right, shoots up. I'm excited. Okay, as soon as it falls right back down, it has to give off some energy. Okay, if you think about when you have too much energy, you got to kind of run around and, give off energy. Well, when that electron falls right back down, it gives off a photon. So out comes the photon. Okay, and a lot of times we see the photon as visible light. Now the energy of the photon is equal to the difference in the energy of the states of the atom. I'm going to show you a ladder analogy here in a couple minutes that hopefully will illustrate that a little bit. Excuse me. Now, since only certain frequencies were emitted, the differences between these states must be constant. So in other words, they're essentially, if you think about a video game, when you conquer level 1, level 2, level 3, level 4, etc., there are these different energy levels, and the distances between them has to be constant. It's not this continuous change, which again, it's heady. We'll explain it to you. Okay, so that led to the Bohr atomic model. Niels Bohr came along in 1913, and if you remember, the last update we had to the atomic model was 1911. Rutherford again said we had a positive nucleus with all of these electrons, negatively charged electrons, randomly placed. And the question they were trying to answer now is, where were these electrons? If you go back to the beginning of this unit, that's what we were trying to answer. Now, what Bohr did is he linked hydrogen atoms, the hydrogen atom's electron, with its emission spectrum. And he said, okay, if we look at it this way, then the electron can only circle the nucleus in certain paths, which each have a certain amount of energy, which a lot of times that's why the Bohr atomic model is also referred to as the planetary model, because it was a very easy model for people to understand, because it essentially meant we had a nucleus in the middle, and then we had all these different orbits, just like, and this isn't totally obviously to scale, but all these different orbits with different energy levels, and the electron could travel in any of those orbits or paths, which again made sense because it was very similar to the planetary solar system model that we have. So a lot of times the planetary model is also, or the Bohr atomic model is also the planetary model. All right, now just to kind of give some more understanding to this, is that an electron can gain energy by moving to a higher rung on the ladder. So here's where my electron's starting. It gains energy and it becomes excited. It doesn't want to stay there. Okay, so in order to come back down, it has to lose some energy. And again, it does that by giving off photons. A lot of times photons of light, but photons of energy. And electrons, again, will lose energy by going down. But if they stay on the same step, it's not gaining or losing. Okay, it's just staying, has the same amount of energy. If this electron wants to stay down here at the ground state and it's going to hang out here for a while, it's going to have the exact same amount of energy. Okay, now what that looks like for the planetary model of the atom is that if we think of this diagram in two parts, over here we have part one, where energy is absorbed by an electron. So here comes the energy. It excites this electron. Okay, so it takes it from an energy level of 1, because it was traveling in this path, to an energy level of 3. Okay, because it moved up essentially 2 energy levels. Now if that electron is spinning around, remember it doesn't want to be excited, so as soon as it can, it's going to drop back down. It may drop all the way back down to 1, may only drop back down to 2. It's going to drop back down, and when it does that, it's going to give off, okay, some light in the form of a photon. And so that's, we kind of think of it as the first is the energy absorbed. It gets excited, doesn't want to be there, comes back down, and it gives off light. So that photon that it gave off, the photon released has an energy equal to the difference between the initial and the final energy orbits. So if we looked at this one, this photon that would be given off would be equal to the difference between this level 3 and this level 2. Again, it's going to take a few times for this to process and for this to make sense. Just bear with us. Okay, like all good models that we had, there were some problems with it. Problem number 1 is it didn't work for any atom besides hydrogen. Well, that's a problem because, we've got 92 naturally occurring types of elements that are all different types of atoms because they have different numbers of protons. So for anything past 1, we were up a creek. And then secondly, it did not explain the chemical behavior. Okay,